everyone out?
Sorry about that. I just realized that I was muted the whole time, so we're going to restart this problem. So for Bf3, count our valence electrons. 3 plus 3 by 7. This is going to give me 3 plus 21 electrons, which is 24 electrons. So this will help us figure out the Lewis structure, which will give us its geometry, and then we can cancel out dipole moments to determine whether it will be polar or nonpolar, depending on the electronegativity differences. And so if we start with this skeleton and fill in fluorine's octets, then we get 6 by 3 plus 3 by 2. This is going to give us 18 plus 6, which is our desired 24 electrons. Now let's double check our formal charge. On the boron, we will have 3 valence electrons minus the 3 electrons in each of those bonding pairs, giving us 0. On the fluorine, we will have 7 valence electrons minus the 6 in lone pairs minus the 1 in that bonding pair, yielding 0. And so this is going to be our best structure because we've minimized the formal charge and all of our valence electrons are taken care of. And so now its steric number is going to be equal to the number of bonding pairs plus the, so initial bonding pairs plus the lone pairs, and that's just going to be 3 plus 0, which is 3. And its notation will be AX3. So when you go to the VSEPR chart, its steric number is 3, so that's our electronic geometry, so trigonal planar. And its molecular geometry will account for how many lone pairs it has. It has 0, so it's also trigonal planar. Now once we begin checking out our dipoles, fluorine is more electronegative in both cases, in all cases, sorry. And so this is how our dipoles would look. And then for these two, they are both at an angle of 120 apart, which is 60 degrees from directly below the boron. And so their angular components will cancel. So these two, x1 and x2 will cancel, and y1 and y2 will add. And they'll actually add to give you a dipole that is exactly equal to the dipole that is pointing up, and these two will cancel out. And so you will be left with a 0 dipole moment, which will indicate that you have a non-polar molecule. Okay, on to the next option. So this can be rewritten in the form of this. And this is C2H2F2. So this is an alkene that's been substituted with 2 fluorines. We don't need to, its Lewis structure is already given to us. And so we just need to figure out the steric number for each of these. And so this has 3 groups attached to it, the F, H, and the C. So this will be steric number of 3, AX3 notation. This one will also be the same, so it's going to be AX3. They're both sp2 hybridized is what that means. And so that means they'll both have a trigonal planar look. So if you just draw one first with the F and the H, a double bond, and then the other one with the H and the F. And so if you just rotate that by 90 degrees, you get what they've shown you here. And so they've drawn it out the way that the molecule will look. And so from there, we can just figure out how our dipoles will cancel, if they will cancel. Okay, so in this case, chlorine is more electronegative than hydrogen. And so we'll have 2 dipoles pointing that way. And fluorine is more electronegative than carbon. But the difference in electronegativities are not the same. So I'm just going to write the dipole in a different color because they will have different magnitudes. And so what happens here is that for these two, as I said before, their angular components will cancel, yielding just one vector pointing up. And the same thing for these two. Their angular components will cancel because they're equal in the opposite direction. And so we'll get another vector pointing up 2. These two obviously cannot cancel. They will add up to give you an even larger vector. Sorry, an even larger dipole. And so we have a non-zero dipole moment. And this indicates that this molecule is polar. On to the next. We have CH2Cl2, which is similar to what we had above, but there are many ways that we can draw it. We can draw it in the same way that they did before. The dipoles will work out exactly the same. We already know that this is the correct molecular geometry. And so the dipoles will work out the exact same way and will not cancel each other. So this structure, the exact one that I've drawn, is polar. But if you're just given the formula, you can decide to place those chlorines anywhere, really. And so if we instead had placed them here, and again, we need to figure out our dipoles. Oh, my apologies. This is supposed to be pointing towards our carbon. And this is pointing towards our chlorine. And so again, angular components, yes, will cancel, but you will still have a red vector dipole pointing towards the right, added to another dipole, again, pointed towards the right because of the chlorine and because of the hydrogen in this case. And so they will not cancel, and this version will also be polar. Now, lastly, had I decided to draw it in this configuration, then it's a different story. Again, I have my hydrogen-carbon dipoles and my chlorine-carbon dipoles. And in this case, I see that these two are equal and opposite, so they will cancel each other. So equal dipoles in opposite directions. And the same thing with the hydrogen-carbon dipoles, equal in opposite directions. So all of the dipoles will cancel, and I will be left with a zero dipole moment, and that is a non-polar molecule. And so for this one, the answer depends on which configuration of CH2Cl2 you have. If it's drawn for you or you're given the name indicating which one it is, then you can definitively say polar or nonpolar. But if you're just given CH2Cl2, then you just need to write out all three. Let's move on to D, where we've been given something similar to B. It's B practically flipped. And so quickly you can tell that it is going to be polar, just like B. But again, you can decide to draw out the dipoles. Fluorine-carbon going to point towards the fluorine. Carbon-hydrogen going to point towards the carbon. Again, the dipoles will be of different magnitudes. And so this will, these two, their angular components would cancel, yielding one pointing downwards. Same thing with the fluorine, would be left as one pointing downwards. And so, of course, that will yield a non-zero net dipole, and this will be, again, polar, just as we had expected. And that's going to be it for this question. Okay, next up, we'd like to figure out which one of these reactions are redox. And so we need to understand what a redox reaction is. So there's two parts to this word, the red and the ox. And the red comes from reduction, and the ox comes from oxidation. So a redox reaction is where both of these are taking place. And a quick way to remember what these mean is to just use the acronym oil rig, and that just means oxidation is the loss of electrons and reduction is the gain of electrons. And so in redox reactions, you will have oxidizing agents. This will be the species responsible for oxidizing another one. So that means it is responsible for another compound losing electrons, which means it must be gaining electrons itself. So it is reduced. So the oxidizing agent gains electrons, and the reducing agent is responsible for reducing another species, which means it is responsible for another species gaining electrons, which means itself it must lose those electrons. And so we're just going to go through A to D and see if we have any indication of electrons moving around between two species. And so with A, we have Al solid plus 3Ag to become Al3 plus 3Ag solid. So we're going to split this into two. We're going to analyze what happens with the aluminum, and then we analyze what happens with the silver. And so with the aluminum, it's going from Al solid to Al3 plus. We know we must balance out the charge, and so we have a net charge of 0 here, a net charge of 3 plus here. If we're balancing that out with electrons, that means we add 3 electrons at the end. Next up, we analyze the silver one, and we get 3Ag plus aqueous into 3Ag solid. Again, we need to balance out the charge. We have 3 plus here, 0 here, so we're just going to add 3 electrons here. And so we can see that there has been a transfer of electrons. Aluminum lost electrons, so aluminum was our reducing agent. And silver gained electrons, so silver was our oxidizing agent. And so A qualifies as a redox reaction. Next up, let's check out B. We have SO3 gas plus H2O liquid to sulfuric acid. Now, by just looking at what this product is, so sulfuric acid is a covalent bond. They're covalent bonds within sulfuric acid. And so electrons are not being transferred because covalent bonds imply that they're sharing electrons. And so already I can tell that there will be no reduction, no loss or gain of electrons. Electrons will simply move between the atoms. And so this will not qualify as a redox reaction. Next up, I'm going to study C. Okay, so this is not a covalent product, and so I can't immediately say that it is not a redox reaction, so I just need to analyze what's happening. So Ba and BaCl2, that becomes Ba2 plus. And then Cl2 is becoming 2Cl minus. And so now I balance that with electrons, so this I'll add 2 electrons. So yeah, I will add 2 electrons so that I have, sorry, not to that side. I have a net charge of 0 here, and I want a net charge of 0 here. So I add 2 electrons to this side. And with the Cl2, I have 2 minus charge here, so I'm going to create a 2 minus charge here, so I can add 2 electrons to this side. And so here I can clearly see that the Ba lost electrons, and so it was my, according to how we've defined it, my reducing agent. And chlorine was my oxidizing agent. And so this does qualify as a redox reaction. Now lastly, let's check out C. We have solid magnesium plus liquid bromine to become magnesium bromide. And so again, this is not a covalent product, and so I just need to analyze what's happening with the electrons to form this ionic bond. So who's losing the electrons and who's gaining them, because ionic implies the loss and gain, or the transfer of electrons. And so I'm going from Mg solid to Mg2 plus. And I'm going from Br2 sorry, Br2 to Br minus. And so, if I want to balance out the charges on both sides, I'll add 2 electrons. So I have 0, 0 on both sides. And here I have 0, minus 2. And so I'll add 2 electrons here. And so based off of this, I can see that the magnesium lost electrons, so it was my reducing agent, and the bromine gained electrons, so it was my oxidizing agent, which means that this also qualifies. And so A, C, and D are all going to be redox reactions. Next up, we're going to want to balance this chemical equation. By balancing, I mean that I have the same number of species on both sides. So we are given CH4 plus N2Cl2 to form ClCl4 plus N2 plus H2. And so already I can see N2 looks fine, Cl2 doesn't look fine, and H does not look fine. And so I'm going to sort both of those out. I'll start with the hydrogen. On this side I have 4. I can't reduce on one side of the equation, but I can add on the other side of the equation. And so I'm going to multiply this side, the hydrogen, by the coefficient of 2 so that I can get 4 and 4 on both sides. Now I see my nitrogen is still fine, my hydrogen is now fine. My carbon is also fine, I have 1 on both sides, but my chlorines are not. I have 2 on this side and 4 on this side. And so, again, I can't reduce on this side, so instead I'm going to add on this side and put a 2 before the N2Cl2. Now I have my chlorine sorted, my carbon sorted, my nitrogen sorted, my hydrogen sorted. I can double check that by writing out the actual numbers. This side, carbon I have 1, hydrogen I have 4, nitrogen I have 4. So as I said, double check, here found an error. And chlorine I have 4. This side, carbon I have 1, chlorine I have 4, nitrogen I have 2, hydrogen I have 4. And so I still need to fix this nitrogen issue. And so I can do that by, remember, I can't reduce on a side, but I can add on a side. So I'm going to multiply this by 2. I'm just going to write it out again. And again, I can just double check to make sure everything's okay. Carbon 1, hydrogen 4, nitrogen 4, chlorine 4. Carbon 1, chlorine 4, nitrogen 4, hydrogen 4. And so I see I have the same number of chemical species on both sides. This equation is now balanced. And that's going to be it for this question. Next up, I want the Lewis structure for Brcn. So as usual, check out my valence electrons. So from Br I have 7 plus 4 plus 5. And this will give me a total of 16 electrons to mess around with. I will have carbon as my central atom, which means I will attach the bromine to the other side and the nitrogen. I can fill in the bromine's octets, in fact fill in everybody's, and see if I have the correct number of electrons. This would imply 6 by 2 plus 4 plus 4, which is 12 plus 8, which is 20 electrons. So obviously I have too many electrons. Bromine I know is in group 7 and group 17, and group 17 have 7 valence electrons. So this configuration is best for it because it's minimized its formal charge, 6 in the lone pairs, 1 in the bonding pair. So I wouldn't necessarily like to mess around with the bromine, and instead I'm going to focus on this carbon and the nitrogen. And so as usual, I'll start fixing things by adding a double bond and seeing if things now work out. I have 2, 4, 6, 8, 10, 12, 14, 16, 18. So again, too many electrons. Remember, don't touch the bromine because its formal charge has been minimized. And so And again, I will add another bond between the carbon and the nitrogen. This actually makes the most sense. Nitrogen tends to like 3 bonds, so that you can get 1, 2, 3, 4, 5. So 5 minus 5, 0. And carbon likes it like 4. And so you can get 4 minus 1, 2, 3, 4, giving you a 0, 2. And so this would be our best structure. If you'd like to double check the formal charges, you'll see bromine, as expected, will have 7 valence electrons minus the 6 in lone pairs minus the 1 in the bonding pair, giving you a formal charge of 0. Carbon will have 4 minus the 4 electrons in bonding pairs, yielding 0. Nitrogen will have 5 minus the 3 in bonding pairs minus the 2 in lone pairs, giving you 0. So formal charges have been minimized, valence electrons have been minimized, so they all have a charge of 0 on them, and this will be your final structure. Okay, next up I want to figure out the molecular shape of If3. So as usual, begin with your valence electrons. I have 7 plus 7 by 3, and this is going to give me 7 by 4, which is 28 electrons. Okay, and then from here, I would have iodine in my middle, and then it makes most sense to have the fluorines around them, because here you can't tell which one can make the most amount of bonds, because they can both make one bond, technically. And so I'm going to fill in fluorines octets, and then count everything that I have. So I have 6 by 3 plus 3 by 2, which is simply 6 by 4, which is 24 electrons. And so I have 4 electrons left over. Fluorines octet is already full. It's already made its optimal amount of bonds, so it makes most sense to place them on my central atom, which is the iodine. And so now all of my valence electrons have been taken care of. I can double check on my formal charge. Fluorine is 7 minus the 6 in lone pairs minus the 1 in the bonding pair, 0. Iodine is going to be 7 minus the 3 in bonding pairs minus the 4 in the lone pairs, giving me a 0, 2. And then, so because the formal charge is minimized and the valence electrons are all taken care of, this is going to be our best structure. And so now I need to figure out the number of terminal groups. And it is going to be 3 plus the 2 lone pairs, and so that is 5. And it would have notation AX3, E2. So terminal atoms represented by the X, and E is the lone pairs. And so from this, I just go to my VSEPR chart. So to find the electron geometry, it will be dictated by the way electrons are generally arranged around your central atom. So you're not really taking into account which electrons are in bonding pairs or which electrons are in lone pairs. And so it's just the basic geometry that you would get down to if there were no lone pairs. And so if you just had 5 groups. And so that would be trigonal bipyramid. And the molecular geometry will now account for which ones are bonding pairs and which ones are lone pairs. And it will describe how the molecule, the 1 iodine and 3 fluorines, would look. So when you're not thinking of these 2 lone pairs. And so it would be, you come down to the 5, and then you account for how many lone pairs you have. I have 2. So it's going to be T-shaped. And so if I drew it out, what it should look like is the iodine. I have my 3 fluorines. And then towards the back, I have the first electron pair, and towards the front, I have my second electron pair. So it's called T-shaped because of just its general look. The three groups that you can see are arranged in a T sort of shape. All these other two look seesaw-ish. But you focus on the main three, so T-shaped. And so the molecular shape is a T-shaped. Next up, we want to balance chemical equation for the combustion of methanol. Combustion can be defined as simply the burning and oxygen of a hydrocarbon. And so the only product should be water and carbon dioxide. I only have carbon, oxygen, and hydrogen available to me, according to its definition. And so, with that in mind, methanol has the form CH3OH. I am burning it in oxygen to produce CO2 and H2O. Next up, I want to balance it. So I begin with my hydrogens. I have 4 on this side, so I can multiply this by 2. Carbons, I have 1, I have 1. Now I begin balancing the oxygens. I have 1, 2, 3 on this side. On this side, I have 4. So I can get this to the same number by multiplying this O2 by 3 over 2. 3 over 2 by 2 is 3 plus the 1, 4. Next up, I like to get rid of this fraction, and I can do that by multiplying the entire thing by 2. And so it will become 2 CH3OH plus 3O2 to yield 2 CO2 plus 4 H2O. And we only do this because we tend to not like fractions in our balanced equation. And so we can now double check. Carbon, I have 2. Hydrogen, I have 4 by 2, 8. And oxygen, I have 2 plus 6, 8. Now I check out this side. Carbon, I have 2. Hydrogen, I have 8. Oxygen, I have 2 by 2, 4 plus 4, 8. And so my chemical species match and everything is therefore balanced. So that's going to be your final answer. Okay, next up, we want to figure out the total number of valence electrons in CH4. To figure that out, I count the valence electrons for each individual atom. Carbon gives me 4. Hydrogen gives me 1, but I have 4 of them, and so this is going to give me 8. If I wanted to draw out the structure, I would have carbon as my central atom because it can make the most bonds. And the hydrogens around it, I just double check my valence electrons are all fine, 2, 4, 6, 8, and everything is. And so the total number of valence electrons is 8. And that's going to be your final answer. Okay, next up, I'd like to find out how many orbitals are there in the third shell and show the orbital diagram for nitrogen, sulfur, and bromine. So, the answer to this question lies in your quantum numbers. And so you have n, which is called the principal quantum number, and n can take any value from 1 to really infinity if you wanted it to. L is called the angular momentum quantum number, and L can take any value from 0 all the way until n minus 1 is the highest value that it can take. ML is called the magnetic quantum number, and it can take any value from negative L all the way including 0 to positive L. MS is the spin quantum number, and it can take values of plus 1 over 2 and minus 1 over 2. So this comes into play, like, for example, where I have helium, so it has 2 electrons. In my diagram, that means I have 1s2. And so that means 1s2, and it would be my 1s. This 1 is n. This s is equal to L. So it's when L is equal to 0. Remember, if n is 1, L can only be equal to 0. And then the number of orbitals I have would be dictated by the magnetic quantum number. And so L is 0, that means ML can only be 0. So the label for this one would be ML is equal to 0. If I have 3p as another example, this means that my n is 3, my p is my L quantum number, so L, and it's specifically when L is equal to 1. And when L is equal to 1, ML can take values from negative L, so negative 1, 0, and 1. And that's actually how I label these three, negative 1, 0, 1, and then the spin would be positive 1 over 2, negative 1 over 2, positive, 1 over 2, negative 1 over 2, positive, negative. And so these four quantum numbers just dictate your labeling of that energy diagram, and that the energy will be dictated by the quantum numbers. And so if I have n is equal to 3, how many L values can I have? So L will tell me how many orbitals I can have. And so L would be equal to 0, 1, or 2. 0 is S, and for S, when L is equal to 0, ML can only be equal to 0. And so you only have one orbital. When L is 1, recall ML can be negative 1, 0, or 1. So I'll have 3 orbitals here. And lastly, when L is 2, ML can be negative 2, negative 1, 0, 1, and 2. And so I have 5 orbitals here. And so namely, that would be your 3s, your 3p, and your 3d. So the 5 that I discussed, when L is equal to 2, this is the d orbitals. When L is equal to 1, these are the p orbitals, they are 3. And when L is equal to 0, that is the s orbitals, and they are 1. And so that will all add up to 9 orbitals in the third shell. Okay, next up, I'd like to draw an orbital diagram for nitrogen, sulfur, and bromine. And so I can begin by just writing out their electron configurations. So just quickly look at the periodic table. Nitrogen is going to be 1s2, 2s2, 2p3. So 1s2, 2s2, 2p3. The next one they ask for is sulfur. So sulfur is right here. So again, just count it out. 1s2, 2s2, 2p6, 3s2, 3p4. And lastly, I believe the last one is bromine. And bromine is right here. And so its short configuration would be AR in square brackets, and then I'll only count along this line. But I'm just going to count from the beginning so I can have the entire diagram. 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. And so in actuality, this 3d10 is supposed to be here, but just because of the way that the periodic table is built, when we write out our structure according to the periodic table, this is what you get. But bromine technically has 7 valence electron, these 2, and these 5. So now I begin with nitrogen's diagram. I will have energy going up that way. I begin with my 1s2, and then I will have my 2s2, and then lastly I have 2p3. So 1, 2, 3. Next up I do sulfur. So again, I'll have my energy going up that way. I begin with my 1s, and then I have 2s, and then 2p, and then 3s, and then 3p. And that's going to be it for this one. And then lastly, I will have bromine. So again, I have my energy going up that way. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, but as I mentioned, this 3d should technically come before it. The reasoning why is just because the energy spacing between 4s and 3d shrinks as you go down the periodic table, and so at a certain point they actually cross each other, and 3d now goes under the 4s, and that actually happens around scandium, and so that's why bromine only has 7 valence electrons. But of course we can't tell you that with the periodic table, because that would place this group here, and that isn't technically correct because the crossing happens at scandium. And so because there's no way to notate that crossing in the periodic table, it isn't necessarily included. And so we're going to have 3p6 and then 3d10. And then your 4s2. And then your 4p5. And so the orbitals have different energies depending on their s and n values. That's going to be because of the way that multiple electrons interact with each other, because of electron repulsion and shielding, which can also be called screening. And so in the solution given here, that isn't accounted for. It's given in the hydrogen-like fashion where all of the orbitals are of the same energy. For hydrogen, that is true because you have one electron. One electron can't shield itself, but for elements where you have many electrons like this, you will have shielding, and these will not all be degenerate or at the same energy. And so this is going to be more accurate than what you have here. My apologies about that. For our next question, we'll be looking for the molecular geometry of NH2-, and we'd like to use Vesper to justify our answer. So as usual, we need to begin with the Lewis structure, which begins with the valence electrons. So we have 2 from the hydrogen, plus 5 because of the nitrogen, plus 1 because of the charge, and this will give us 8 electrons to work with. And so we will have nitrogen as our central atom, because it can make 3 bonds. And then we have 2 4s so far. We can't put them on the hydrogen. Hydrogen doesn't have the space for that, so it makes the most sense to put it around our nitrogen. This will lead us to the conclusion that we have a steric number of 4, and it would be AX2E2. So we just go to our Vesper chart. The electron geometry would be tetrahedral. And the molecular geometry will account for the fact that some are lone pairs, and it will be bent or angular. So bent is the more common name. So if we're just to draw that out, we would have N, H, and H in the plane, and then you would have one pair of electrons behind and one pair of electrons coming out of the plane. And so the answer to this question is bent. Sorry, I forgot to include that the negative charge is on nitrogen. You can see that by just testing its formal charge. Hydrogen is 1 minus 1, 0. Nitrogen is going to be 5 minus the 2 electrons in bonding pairs minus the 4 in the lone pairs. And that's going to give you -1. And so that's it for this question. Your answer is bent. Next up, we want to look at the hybridization of iodine in IF3 and IF5. So let's start with IF3. Valence electrons, I have 7 by 3 plus 7, which is just 7 by 4, giving me 28 electrons. So I'd have my central iodine, as we did before. Fill in the octets of all the fluorines. And this would give me 6 by 3 plus 3 by 2, which is just 6 by 4, so 24 electrons. Clearly not my 28. The only place the other 4 electrons can go is on the iodine. And then now that my valence electrons are all taken care of, let's just double check on my formal charges. Fluorine is going to be 7 minus 6 minus 1, 0. Iodine is going to be 7 minus 3 minus 4, 0. So they're both have a formal charge of 0, and this is my best structure. Now I check the steric number. I have 3 attached groups plus 2 groups that are lone pairs. So my steric number is going to be 3 plus 2, which is 5. Its notation will be AX3E2. This is my number of bonding pairs, my number of lone pairs. And so now that I have that, I can go check its geometry. This VSEPR chart does not list that, but another good way to remember it is that my total orbital should add up. And so I usually have 1s orbital available to me, 3 p, so right now I have 4, and then I'm going to need to add 1 from the d in order to get all of those exponents to add up to 5. So the central iodine will be sp3d1 hybridized. Now let's check out IF5. And this one has 7 by 6 electrons for its valence electrons, and that is going to give me 42. So I have I in the middle, and my terminal fluorines. Fill in everybody's octet. And so now I've covered 5 by 6 plus 5 by 2. This will give me 30 plus 10, which is 40. So I have 2 more electrons left over. The only place to put them is on the central iodine. And so that's going to be that. Double check your formal charges. For the fluorines, I have 7 minus 6 minus 1 as usual, so 0. On the iodine, I will have 7 minus 5 minus 2, so 0. And so this is definitely our best Lewis structure. And so now I will check the steric number. And it will be 5 plus the 1 lone pair that I have, so 6. Its notation will be AX5E. So the 1 lone pair and the 5 bonding pairs. So its electron geometry is going to be octahedral. Its molecular geometry is going to be square pyramid. And its hybridization, as mentioned before, I only have one s orbital. I have 3p, so far I have 4. I need a total of 6, so I'm going to add 2 from the d. And that's going to be it. So its hybridization will be sp3d2. And that's going to be it for this question. So the first answer is sp3d1, second answer is sp3d2. Okay, next up, I would like the Lewis structure for BH3 and PH3. Do the two molecules have the same electron group geometry? Do they share the same molecular shape? Okay, so let's start with BH3. As usual, begin with your valence electrons. I have 3 from the hydrogen plus 3 from the boron. That gives me 6 electrons to play with. And so I'll have B as my central and then the 3 hydrogens. Right now I have 2, 4, 6, so the correct number of electrons. Formal charges, hydrogen each have 1 bond, so 1 electron in that bond. So that's 1 valence electron minus the 1 valence electron they have inside of that bond, so 0. Boron, it's going to be the 3 valence electrons it has minus the 3 electrons it's donated to each of these bonds, so 0, 2. And so my valence electrons are taken care of, my formal charge is taken care of. And so now I begin with the steric number. It will be 3 because I have 3 bonding pairs, no lone pairs, and this would indicate that it's trigonal planar. And so when I draw it out, it will look basically how I had drawn it before, with angles of 120 degrees between them. And both my E geometry will be trigonal planar. So the way the electrons are arranged around it and the way my actual groups are arranged around it. So the BH3 molecule itself will also be trigonal planar. Let's check its polarity. So I have a dipole going in like that, one going in like that. So because boron is more electronegative than the 3 hydrogens, these two, their angular components will cancel, yielding only a vector pointing up that will be equal to the opposite one, so they will cancel, and the molecule will be non-polar. Next up, we're just going to do the same for PH3. So my valence electrons, I will have 5 plus 3, so 8 electrons available to play with. So I can start with my 3 hydrogens, and I can see right now I have 2, 4, 6, so 2 more electrons left over. I'll place them on my central atom. Now when I come to the, if you want to check each of their formal charges, for hydrogen it is going to be the 1 valence electron minus the 1 electron that is partaking in this bond, so 0. For the phosphorus it will be 5 valence electrons minus the 3 electrons partaking in this sharing minus the 2 electrons in the lone pair, giving me 0, 2. And so this is going to be our best structure. My steric number is going to be 3 plus the 1 lone pair, 4. Its notation will be AX3E. What that means is it will have an electronic geometry of tetrahedral, but a molecular geometry of trigonal pyramid. And so when I draw it, it will look like this. P with my 2 electrons. Hydrogen, hydrogen, hydrogen. Now when I go about drawing the dipoles, I'll have a dipole pointing towards the lone pair. Hydrogen is less electronegative than phosphorus, and so I'll have those 3. Even if these 3 add up to 1, as they will, I'll have 2 different magnitude vectors pointing up, they can't cancel each other out. And so this molecule will be polar. And so let's come down here. Its electron geometry we found was tetrahedral. Its molecular geometry we found was trigonal pyramid. And last to be found that it will indeed be polar. So now let's go back to the questions asked. First up, we're asked if they have the same electron group geometry. Let me just zoom out so you can see everything. Okay, so electron group geometry, one is trigonal planar, one is tetrahedral. So the answer to question A is no. B, do they have the same molecular shape? One is trigonal planar, the other one is trigonal pyramid. Those are two things. Trigonal planar is in the plane, so exactly as I've drawn it. Trigonal pyramid is more like a tripod. That's why I have one hydrogen going back, one coming out, and so it will look oh, it appears I have frozen, but it will look basically like a tripod. And so those two are obviously not the same thing. And so the answer to B is also no. The answer to C we have already found. BH3 is nonpolar, PH3 is polar. So we have nonpolar for BH3, polar for PH3. And that's going to be it for this question. Okay, next up we have oxalic acid that is reacted with sodium hydroxide. We want to find out the molar concentration of sodium hydroxide. So we need to first start off by writing out our reaction. Okay, and so now based off of this, we can see we have a 1:2 ratio between these two. And so if I have 0.147 grams over 126.07 grams per mole, this will yield 0.001168 mole. And so if I want to find out the moles of any sodium hydroxide, I'm just going to multiply that by 2 based off of this relation. And that is going to give me 0.0023320377757 mole. I like to write out the entire thing that way because I'm still using these values, so I want to cause the least amount of decimal error. And so next up, I am told to find the molar concentration. Molar concentration is equal to the amount of moles you have over the volume. I'm told I have a volume of 23.64 milliliters, and so that means my molar concentration will be 0.0023320377757 over the volume that I have in liters. So that is 0.02364 liters. This will give me a molar concentration of 0.0986. And that is going to be your final answer. Next up, the electronic geometry of Bf3. So as usual, valence electrons, 3 plus 3 by 7, 24. B in the middle, surrounded by your 3 fluorines. Fill in everybody's octet. Now I have 6 by 3 plus 3 by 2, and this will give me my desired 24 electrons. My formal charges, fluorine is 7 minus 6 minus 1, 0. On the B, it is going to be 3 minus 3, 0. So this is my best structure. I look for the steric number, and it is going to be 3, notation AX3. If I come to my VSEPR chart, that is going to dictate a trigonal planar electron geometry and molecular geometry, because I don't have any lone pairs in this case. So the best answer would indeed be trigonal planar, and that's going to be your final answer. Okay, next up, I am told that I have a 0.3 molar solution of formic acid, and I've added enough sodium formates to make, the solution 0.1 molar in the salt. Calculate the pH of formic acid solution before and after adding solid sodium formates. So my acid dissociation equation for formic acid looks as follows. And so I'm going to develop an ice table. I'm told what I start with, but because there is some form of equilibrium, since this is a weak acid, I'm going to need to figure out how many moles of H3O plus I have once it does reach equilibrium. And so my initial concentration is 0.3 molar. The change will be minus X. This doesn't matter because it's in liquid. This is 0, 0. I will add X and add X during the reaction. So at equilibrium, I should have X in 0.30 minus X. And so Ka is equal to 1.8 by 10 to the negative 4. And this will be equal to HCO2 minus by H3 plus over HCO2H. And so I can rewrite that as x squared over 0.30 minus x. And this is 1.8 by 10 to the negative 4. Now note that whatever x I get from this will be small, because Ka is a small value. It's by 10 to the negative 4. So if I'm taking away such a small value from 0.30, it makes practically no difference. So in order to simplify our calculations, we're going to forget about this x here, because it will make that much of a difference to a very small number over a large number, 0.3 minus something very, very small. And so that means that 1.8 by 10 to the negative 4 is equal to x squared over 0.30. Solve for x as the square root of 0.3 by 1.8 by 10 to the negative 4. And I get an x value of 7.35 by 10 to the negative 3 molar. And so note the concentration of H3O plus at equilibrium is that. And so in order to find the pH, I'll just need to take the negative log of the concentration of H0 plus, which will be the negative log of my answer up here. And that will actually give me a value of 2.13 as my answer. Now for the second part, I will use the Henderson-Hasselback equation, and that just states that pH is equal to pKa plus the log of HCO2 minus over HCO2H. So now I am told that I've added 0.1 molar of the salt, and so I'm going to include that in this equation to find the new pH. My pKa is 1.8 by 10 to the negative 4 plus log of 0.1, so HCO2, my salt, is 0.1 molar, has been added, over 0.30. And this is going to give me the answer that the new pH is 3.26. So the pH before was 2.13, the pH after you adding that salt is 3.26. And that's going to be your final answer. Just one moment. And so, sorry. Okay, sorry about that. So this is going to be our second last question, and it is asking to write the net ionic equation for the following molecular equations. HBr is a strong electrolyte. Okay, and so for our first one, we have H plus Br minus, since they're an aqueous solution, plus K plus OH minus, because they're also an aqueous solution and it's a strong base, will give us K plus Br minus plus H2O liquid. That I can't separate into their ions. So now I'm going to look if I can cancel anything on both sides. So it's called the Ionic equation because I only want to include the ions that are doing something in my equation. And I can see that the potassium ion is remaining in its same form, potassium ion, and so it's not really doing anything, and so is the bromine ion. And so my net ionic equation will be H plus OH minus to become H2O liquid. And this will be the first one. My second one is I have Ag plus NO3 minus plus Na plus Br minus, because they're all aqueous, going to AgBr, I can't separate it because it's solid, plus Na plus NO3 minus. This one I can separate because it's an aqueous. And so now I cancel out anything that's remaining as it was. NO3 is remaining the exact same, sodium is remaining the exact same. And so my net ionic equation will become Ag plus Br minus 2AgBr solid. And this will be my second one. For my third one, I have 2K plus S, 2 minus, because it's aqueous, plus 2H plus 2Br minus, and this will form 2K plus 2Br minus
plus H2S. It's gas, so I can't separate it into its ions. Now I cancel out anything that doesn't really participate. Bromine doesn't, potassium doesn't, and that will leave me with the net ionic equation S2 minus plus 2H plus to form H2 solid. And then lastly, I have Na plus OH minus plus NH4 plus Br minus to form Na plus Br minus plus NH3, I can't separate it, it's in its gaseous form, plus H2O, I can't separate it, it is liquid. Now I cancel out anything appearing the same on both sides, and this will leave me with the net ionic equation of NH4 plus OH minus to form NH3 plus H2O. And that's it for this question. Next up, for my last question, I want to find out how many valence electrons are in each of these. And so I can do that just using the periodic table. So beginning with zinc. So I see zinc is at the end here of my 3D group. Its configuration would actually look like this. D10. And so the 3D group, as I said before, past scandium would actually be before the 4s, and so I only have 2 valence electrons for zinc because the 3D group is full. It's been, I call it settled in my head, and so only the 4s group is outside of that core, and so I only have 2 valence electrons. For my next one, they're asking for the number of valence electrons in iodine. This one should be quite straightforward. You know it's in group 17. It should have 7 valence electrons. Last up, I am looking for the number of valence electrons for silicon. Silicon, I can see past this core of neon, I have 1, 2, 3, 4, and so I have my 4 valence electrons. And lastly, for iron, I have my configuration as, argon as my closest core, and then I begin filling. I would have 4s2, 3d6. So in this case, yes, the 3d would be below the 4s, but it's not full. It's not settled or stable yet, and so I would have 8 valence electrons. Both of them would contribute as valence electrons, and I'd have 8 valence electrons. And that's going to be it for this question. And those are all the questions I have for you today. I hope you enjoyed today's stream and learned something from the questions. If you'd like to be notified of when we do post again on the channel, be sure to hit the subscribe button and the bell right next to it. If you would like to be able to post questions of your own and see them answered during the live stream, ensure to check out the links in the description, share them with your peers so that we can get a wider variation of questions that students would like answered. This has been Marlyn from OneClass, and I hope to see you next time.